was supposed to be caught up with this, and I am not. So Diels-Alder ends up with, you start with a diene and a dienophile. So a diene is di double bond, right? So diene, and a dienophile, a lot of the times, we do this. Okay, yeah, it's often like a triple bond, often this specifically, or an alpha beta unsaturated ketone. So basically, the mechanism with this guy, one step, all happens at the same time. This guy goes, hey, I want to go attack you. And this guy goes, hey, what if I attack you back? And this guy goes, fine, I'll move over here. And you get this. And then, you know, whatever was attached here. So when you've just got a, when this isn't part of a ring, a lot of times we'll draw dienes like this, but this is oriented wrong for this, right? But we can rotate around this bond, because this is just a single bond. So actually, we can just fix this to turn into this, right? That is just a rotation that's totally allowed. But sometimes we end up with like really ugly rings that I draw. God, no. There, semi-ugly rings that I draw. And this guy is being held in this, there's a word for it that is based on cis. But it's not actually cis. And I don't know if your book even talks about it. S-cis, here we go. This is called an S-cis conformation. S, here. More whiteboard space. S-cis conformation. So we have to be able to get into this S-cis conformation in order to use this diene as a diene in a Diels-Alder reaction. Which means if we've got, if we have this, there's nothing we can do, right? There's nothing we can do to turn this into an S-cis because this is held in place exactly how it is. There's no rotating this stuff because that would be like pointing into the middle of the ring, and you can only get weird stuff like pointing into the middle of the ring if you've got like, generally crown ethers, because you get huge ass rings with those, like 12, 14 member rings, something stupid like that. With those are all sorts of methods. You can get stuff pointing into the middle, but that, not gonna work. That can turn to work, and that can't turn, but it works. So it's a concerted reaction. These three things just sort of happen. In your lab, I'm not sure if this is right, but this is, I know that this is going to be one of the steps to your stuff, because that that is, you're doing a Diels-Alder reaction. So that should be one of the steps to your mechanism. It's just that you guys start with that. O-O-E-T, C-O-O-E-T. So, oh, I used blue, whatever. So when we do this guy, we end up with something not overly, okay, so I'm just gonna draw the hexagon. We get this, C-O-O-E-T, and then these guys are still attached to each other with the carbon in the middle, right? So we're gonna do C double bonded to an O that's got wedge bonds that I didn't center, but that's okay. Yeah? So that's what you guys end up with, and we're trying to draw in those because you know you're going to get rid of CO, and we decided CO looks like this, correct? So I'm going to go with, I'm going to draw that just absurdly large so I can draw the, yeah, we're just going to do this. All right. Okay. I'm going to go with, this guy is going to have to, in order to make that, one of these is probably going to come over and make that triple bond, and it's got to take one of these bonds with it when it leaves. So I'm going to go with that maybe. That should give us CO gas piecing out. Then what happens is we end up with these electrons hanging out right here that don't have anywhere to go. This guy has an empty orbital that needs to be filled up, and all the carbons next to those guys are sp2 hybridized. That was supposed to be an arrow, sp2, sp2. And these guys are currently sp3, right? 1, 2, 3, so they've got an H, so these guys still have hydrogens. So I think what happens is you're going to end up with the other electrons just going, hey, you know what? If we're sp3 now, but this guy's all of a sudden got an empty orbital, so what if we just make that an empty p orbital, and it shares these electrons, and we do some resonance and it becomes like a pi orbital, and what if this guy, this lone pair, goes into a p orbital, and we did this? That would give us our that. This is my guess. This is Diels-Alder. This is not a guess. That's a diene. This is a dienophile. It likes dienes, and that's my guess for that. So, yeah. All right. I'm tired of chapter 19. Let's be done with it. Okay. electrosynthetic analysis. So, the characteristic functional group created by alkylation of an enamine is a carbonyl compound with an alpha carbon that has a group that could be derived from an SN2 reaction. What's an example of that? It used to have a leaving group. How can we tell if it used to have a leaving group if we're trying to come up with? We don't have this, so we can't see that it's a leaving group. So this is just, I mean, I guess this alpha carbon is sp3 hybridized. It doesn't have any double bonds, so there's that. I guess that's mostly, yeah, I guess that's basically going to be it. Because that's the only real limitation with SN2, right? What's up?
Did we do acetylation?
We did not do acetylation, but acetylation would be, where's my, oh, sorry. I have a whole slide on that and didn't see it. Yes, we have acetylation. We can do this. This is a thing that can also happen. So acetylation, we were going to have that guy, and let's use the same base down here for the enamine. And we're going to add, so we no longer get to play with aldehydes and ketones. Now we have to have a good leaving group. So this guy is only going to happen if we use an acid chloride or an acid anhydride. Those guys are hella reactive, so we can use those. But if we're doing acetylation, that's all we can do. So we're going to do, we're going to take these guys, I guess let's identify nucleophile electrophile first, right? So this is the electrophile with this being where the electrons come from. This is this is the nucleophile, sorry. This is the nucleophile. It has electrons. This is the electrophile. Nucleophile, words are hard. And this is our leaving group, right? And if this was an anhydride, then it would just be, this whole thing would still be our leaving group, right? I'm going to do it with chloride because, one, your slides have that, and two, I don't want to draw the rest of that. So we do a nice little attack, and we do that, and we get, and when we do that, we've got, lone pair over here. We've got this lone pair that's going to go, hey, don't worry, carbon, I got your back. You can still have an octet. I'll just be positively charged. Don't worry about it, I don't mind. Then we're going to have, this is our new bond. That guy. And this carbon has CH3, an O minus, and a Cl on it, which is super easy. We just do a nice, hey, you know what? Get out of here. And we get tiny ring. have this. Okay, so this is your slides have this iminium chloride intermediate. That's what we've got here. Yeah, iminium chloride because they seem to keep trying to make us pretend we care about the counter ion, but we don't, so iminium cation, then we don't care what it is. And then you're just going to do water acid workup, at which point you're going to attack here, and I don't want to draw all of that again because we've got content to get through, and so we're going to do eventually this guy, HCl and H2O, is going to replace that double bonded nitrogen with a double bonded oxygen, right? And this was here originally, this was here originally, and this is our new bond. Yes? Okay. Now it's a little easier to go through retrosynthesis, right? Because we've either got alpha to our carbonyl. We've got a carbonyl and alpha to it. We've got an SN3, an sp3 hybridized carbon. I'm trying really hard, but I can't think of any other criteria for had to have been formed, had to be able to be formed by an SN2 reaction. Because yes, we need a leaving group, but like, we're doing retrosynthesis, the leaving group left, so you just get to decide if there's a leaving group, right? So basically, the bond we end up making, not right here, right? This isn't our new bond. Our new bond is carbonyl alpha, then the new bond, yeah? So that's the bond we break, right there, after the alpha carbon, and then all of this stuff gets some sort of leaving group on there, and we add one of these guys, because it's kind of, sort of protecting group, sort of makes the reaction go kind of a thing, right? It's just sort of there for a little while, but makes the reaction do its thing. Otherwise, if we did acylation, we're going to have beta ketones, two beta ketones beta to each other, I don't know. You're going to get to pick which one you want to break, because it doesn't really matter, right? So in this case, they decided to break it here and put a chlorine there. You could also put make this an acid anhydride. But if you're going to make that an acid anhydride, you should probably make it symmetrical and not make it like an acid anhydride of, acetic acid or something like that, just because, well, it's just better if you've only got one type of carbonyl. Otherwise, other stuff happens and purification gets dumb. So they cut it here, did that, and then whatever's left over is this, made that a ketone, and we have that we put on and then take off. But you could also easily cut it right here. Yeah, you could totally cut it right here and make this CH3COCl, and then make this a CH3. You could totally do it that way too. So, when you're doing retrosynthesis, you have one place you've got to cut the bond, right? I mean, cut one of these guys off, right? I don't know. I think it's probably easiest to do, yeah, it's easiest if what you end up with is symmetric. That makes sense. It's easiest if the thing that is going to be your, start as your ketone, and get this become an enamine. It's easier if that's either symmetric or only one side of it has alpha carbons. So in this case, we could do either way, right? Because if we cut it here, then that's, what do we end up with here? Not an H because we don't have a, oh no, yeah, this is a chlorine, right? CH3Cl here, if we reverse it, and this can be a CH3, and we can still do that backwards because the other alpha carbon has no hydrogens, right? So if we wanted to take this guy with a CH3 there and make that be enamine and have this without that second carbon and have a Cl, we can do that. Normally, it's going to be easiest to have a symmetric carbonyl. Okay. This is where I was trying to decide. Okay. We have till 9:40. But it's still. Okay. We will go through, we'll go through acetoacetic ester synthesis, fine. Yeah, I can make it short, I think. Okay. Luckily for us, we don't actually do a mechanism with this. So if you were looking at exam 2 or practice exam 2, you'll notice that I had some like, oh, you can either draw me the mechanism of this, or you don't even have to do a mechanism, just draw me the stepwise synthesis of this. This is one of the stepwise syntheses that I had as an option to get out of drawing the mechanism. So, basically, for an acetoacetic ester synthesis, this is going to be useful for monosubstituted and disubstituted acetones of the following types. So, ethyl acetoacetate, that guy, acetoacetic ester, is this, we take this part of it, and we can attach R, a monosubstituted acetone, R and R prime, a disubstituted acetone, basically. And this is to the alpha carbon. So we know which alpha carbon because we're starting out with this, which if I draw not the way they've drawn it, because the way they've drawn it just doesn't, at least to me, it's not quite as obvious. But if I draw it this way, then it's much easier to see that these two hydrogens are like all of the acidic, right? Like these hydrogens are acidic, they're alpha to a carbonyl. These guys are double alpha. They're alpha to 2 carbonyls, so if we're gonna deprotonate anything, it's gonna be these, not that. Until all of these are gone, we're not gonna bother deprotonating anything over here. So, we can basically either substitute onto here once or substitute onto here twice. That's the bond we're eventually going to end up breaking. We're going to kick that shit off. And then we can attach stuff to here. So, okay, for this target molecule, monosubstituted acetone. We know, whenever we're doing retrosynthetic analysis, we know that much of it is from the ethyl acetoacetate. So we have 1, 2, 3 more carbons that we need. Those are the R group of a monosubstituted acetone. If we want to do that, we are going to start. Let me draw our target molecule up here. Wait, where did my target molecule go? Oh, I have this in my head. This part comes from one thing, this 1, 2, 3 comes from the other. All right, so our first step is we have, and it is much easier to draw our ethyl acetoacetate. That's kind of wavy, but it's fine. There's clearly a carbon here, right? That's not too curved. Okay. That. And this is a case where we can draw this as COOET, because, well, this stuff doesn't do anything except leave, so, okay, who cares? It doesn't really do a whole lot of participation. We take this and we deprotonate it. We're not going to deprotonate it with NaOH, right? Because, well, NaOH is going to give us, that could undo this ester, right, and turn it into a carboxylic acid. So we're going to do the